Good morning. We're going to be looking at continuing our work on our Radians work from year 13, looking at how we use Radians when we're dealing with sectors and segments. I've got a drawing of a sector here, a chunk of a circle, radius r, angle theta, which could be in either degrees or radians. And then we're going to be looking at how to work at the arc length and the area of that chunk. There's a few things we need to know, formula-wise, but let's show where they come from. If I want the arc length, it's a fraction of the circumference. So if theta is in degrees, it's theta over 360 degrees times by 2 pi r. Well, all that becomes, when I do theta times 2 pi over 360, pi over 180 times the radius. Well, if theta is in degrees, how do you change from degrees to radians? You times by pi over 180. So all this is r theta when theta is in radians. So my arc length is simply the radius times the angle in radians. And similarly for the area of the sector, it's a fraction of the circle. So it's a fraction of pi r squared. It's theta over 360 times pi r squared. And in the same sort of way, it becomes theta times pi over 360 times r squared. And I'm going to split the 360 up as 2 times 180. So I've got that pi over 180, which is how I convert from degrees to radians. And we say that is the same as a half r squared theta. So we've got our formula for arc length, we've got our formula for area of a sector, and that's what we're going to use. So if I've got a setup like this first example here, I've got a circle, O, P and Q are 2 points on the circumference of the circle. There's an angle formed from P to O to Q of 1.6 radians and a radius of 15 centimetres. And the question asks for the arc length of PQ. It actually asks for the minor arc length because you've got two of them. You've got a little one around that way and a big one around that way. And that'll be the major arc length there. So what you'd have to do if you want that one is work out 2 pi minus 1.6 and then use that as your theta angle. But all I'm going to do here to work out the minor arc length is get the radius r 15 times by 1.6 equals, I'm feeling lazy today, so 15 times 1.6 equals 24 centimetres, because it's length. Perimeter of the shape from O to P to Q and back again is simply the arc length, 24, plus 2 lots of 15. And I think I'll avoid using the calculator for that one to get 54 centimetres, because I've woken up at last. Area is a half r squared theta, so it equals, I'll put equals down here, a half times 15 squared times 1.6, and press buttons again. I could almost work it out, but 1.5 times 15 squared times 1.6 equals 1/8. Of course it does. And because that is an area, centimetres squared. Nice and straightforward so far. So that's how we deal with arcs of circles and areas of sectors. The heading though was sectors and segments. Now a segment is like a chunk of Terry's chocolate orange. It's this sort of shape here with the straight edge and the curved part there. And your common question is to find the area of that shaded segment. So how I'm going to do it in this case, with this example, I've got a circle of radius 6. I've got an angle in terms of pi over 5. So I don't need my radian symbol because we assume, because it's in terms of pi, that it's a radians angle, and I want that shaded thing there. So all the shaded bit is going to be the area of the sector minus the area of the triangle. So the area of the sector is a half times 6 squared times pi over 5 minus the area of the triangle. I'm going to use a half AB sine C and a half A and B are both 6 and 6, so it's going to be 6 squared and then times sine of pi over 5. And I can actually, sometimes you'll see this algebraically as a half r squared theta minus sine theta. So it's pi over 5 minus sine pi over 5. And press my buttons, so a half times 4.5 times 6 squared times bracket shift pi divided by 5 minus sine shift pi divided by 5, 2 brackets there, make sure I'm in radians. I've got 0.72, it's not going to be that big, 0.73, and that's going to be centimetres squared. Okay, and as a check, these things are going to be fairly small. A half of 6 squared is 18, pi over 5 is going to be, let's have a check just to make sure, with a decimal, 0.62, and sine of pi over 5 is going to be fairly similar to that, 0.587, so it's only going to be a difference of about 0.04, 0.95, and times that by 18, yeah, and we're there or thereabouts, and it sounds about right there. And that's how we find the area of a segment of a circle. Okay, the third example is a simultaneous equation. We've got a chunk of a circle, radius r, an angle of theta. It's a reflex angle, so I'm going to be expecting an answer bigger than pi. They're going to give me what the arc is, 24 pi centimetres. They're going to give me what the area is, 216 pi centimetres squared. And because everything's in terms of pi, I'm expecting pi's to cancel out and give me nice-ish numbers. So all I do, I set up my equations. The arc, 24 pi, equals r theta. And then 216 pi is a half r squared theta, which is a half r times r theta, or half r times 24 pi. And hey presto, I can get the pi's cancelling out. I can say that the half and the 24 makes 12, so r will equal 216 divided by 12, whatever that is, 216 divided by 12, which is 18 centimetres. And then stick it into the simpler one there, 24 pi equals 18 theta, and theta equals 24 pi over 18, and cancels down to 4 pi over 3, which is a reflex angle. And that's nice and straightforward. You can do the simultaneous part however you want to. I could have divided them and cancelled down, had a fraction, cross-multiplied, but it was nice to rewrite the expression here, so I've got that r theta on its own. I can just substitute that into there. I've got an equation in two unknowns, and I've gone down to, sorry, two equations, two unknowns, one equation with one unknown, and solved it and stuck it back in the simpler one. If I have time, I can check that this r and this theta satisfies 216 pi as well, but I might leave that in an examination till I've finished the paper. I can come back and then think I've got time to actually check on my answers in a bit more detail.